Welcome back to Interview Preparation Guide. This is part one of the sorting algorithms, and we'll today discuss some very interesting problems that often show up in interviews. Let's first start with the definition of the problem, and then we'll see how we can solve it. Okay. So the problem statement goes like this. Suppose you want to send a team of Indian athletes or some games to Olympics, and we want to choose the best two players. Okay, we choose the best two players. And this is a two-player game. The rules of the game are like this. Okay, this is the rules. Okay, and this is a transitive game. That means A beats B and A beats B and B beats C implies that A beats C as well. Okay, so this is the only key rule. So now the goal is to find out the minimum number of matches. Okay, so we need to find out the minimum number of matches that is required to determine the best two players, the champion and the runner-up. The goal is how can we find it? Now this is a very interesting problem. Now this is a two-player game, so one very natural approach is to determine how many games we need to find out the best player. Best player is never beaten, and we have this transitivity, so we just have to make sure that he is never beaten. So we can partition it into a set of two players. So there are 128 players, so we can make them into two groups, and let's see which all groups we are looking at. So 128 players, that means 128 divided by 2, 64 groups. Okay, so in the first iterations 64 sets of two players play, and then in the second iteration we'll again have 64 by 2, 32 groups, and then we'll have 16 groups, because all we are doing is taking the winner, take the winner from here, take the winner from here. So then we have 8, 4, 2 and 1, right? And this is the guy, the best player. Now this is obvious because this is transitive, so anybody who lost in these games, the players who lost, they cannot beat any players who won, who lost. Okay, so first 34 eliminates 34 losers, then 32 losers, 16, 8, 4, 2 and 1. The last one is definitely the winner. So the number of games is really, n by 2 plus n by 4 plus up to 1. So in this case it's actually 96, 112 and 8, 120, 24, 26, 27. So 127 games. Okay, so I can get the winner in 127 games. Now what about the second best player? So the transitivity is a key note here. Now for the second best player, okay, let's see how can I do that. So how many matches did the winner have to play? The winner was part of this game, this set. He must be part of this set. He must be part of this set. 4, 5, 6 and 7. So the winner played It's 7 games. In general, it will log of n plus 2, where n is 128. 7 games, right? Now for the second best player, all he has to do is to be able to beat all the 7 losers, and that's what it is. So all these 7 losers have to be played against. So the second best players can be determined in only 7 games. So those 7 losers are the candidate, because those are the ones whom the champion beat, right? So whoever is the second, whoever lost in the final, the person who lost the final, okay, need to play 7 more games. Needs to play 7 more games. 7 more games, right? So the answer is, if we're really looking for the right answer, the answer is here. You need log of n plus 2 plus, okay, so log of n plus 2 games for the winner that he plays, and then you have n minus 1 games overall, right? Because you got 7 players that came out of this, which is actually part of this. So these 7 players need to play against the person who lost in the final to determine the runner-up. And because this is transitive, you don't have to play all sets of games, just 1 game at a time is fine. So you need log n plus 2 plus n minus 1. So in this case it was 127 plus 7, 134 games. Okay, so it's a very interesting problem because there are a lot of tricky observations here. So hope you enjoy it. We'll be back with more problems. Bye.